Section 7.1, Basic Trig Identities. So, an identity is a statement of equality between two expressions that is true for all values of the variables for which the expressions are defined. An identity involving trigonometric expressions is called a trigonometric identity. If you can show that a specific value of the variable in an equation makes the equation false, that's called a counterexample. It only takes one counterexample to prove that an equation is not an identity. That's why proving that something is not an identity is easier than proving that it is an identity. To prove that it is an identity, you have to show that that's true for all values of the variable. To prove it's not an identity, you only have to show that it's not true for one value. Much easier. So, are these identities? X squared minus y squared equals x plus y times x minus y. This is an identity because this is the same as this for all values of x and y, right? This is the FOILed form of this, or the factored form. So this is always true, right? If you multiply x plus y times x minus y, you always get x squared minus y squared. X plus 3 equals 7 is not an identity because if I say x equals 5, 5 plus 3 does not equal 7. So there is a value of x for which this is not true, so this is not an identity. All right, so with trig functions, prove that sine x cosine x equals tangent x is not a trigonometric identity by producing a counterexample. So any value of x that we can plug in here where sine x times cosine x does not equal tangent x would be a counterexample. In this case, I'm going to pick x equal to pi over 4. So plug that in, sine pi over 4 times cosine pi over 4, and see if that's equal to tangent pi over 4. Sine pi over 4 is the square root of 2 over 2, and cosine pi over 4 is the square root of 2 over 2. And if we multiply those together, we get 2/4 or 1/2. Tangent of pi over 4 is 1. 1/2 does not equal 1, thus this is not an identity. So x equals pi over 4 is a counterexample. Identities that can be derived as 1 over something are the reciprocal identities. So sine is 1 over cosecant in the same way that cosecant is 1 over sine. Similarly, cosine is 1 over secant, the same way that secant is 1 over cosine. And tangent is 1 over cotangent, and cotangent is 1 over tangent. We also have identities that can be derived from dividing one function by another. These are the quotient identities. So tangent x is sine over cosine, and cotangent x is cosine over sine. The Pythagorean identities are probably the most important. These are derived from the Pythagorean theorem. Right, on your unit circle, right, the x distance of any point on the circle is the cosine of some angle theta, and the y distance is the sine, and the hypotenuse is 1. That's why it's called the unit circle. And if you do Pythagorean theorem, cosine squared plus sine squared equals 1. and that is the first of the Pythagorean identities. If we take this sine squared theta plus cosine squared theta equals 1, and we divide everything by cosine squared theta, right, sine squared over cosine squared would be tangent squared. Cosine squared over cosine squared is 1. 1 over cosine squared is secant squared. So we get the second identity by dividing the first one all by cosine. If, instead, we divide everything by sine squared, sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. And 1 over sine squared is cosecant squared. So we get the third identity by dividing everything by sine squared. All right, so if secant theta is 3/2, find cosine theta. All right, cosine theta equals 1 over secant theta. So 1 over 3/2 is 2/3. The reciprocal identities are called that because you get the reciprocal. You flip the fraction. If cosecant theta equals 4/3, find tangent theta. We don't have an identity that relates cosecant and tangent. There's a couple of things that we can do here. One thing would be if cosecant is equal to 4/3, right, then sine theta is 1 over cosecant theta, which would be 3/4. And then we could do the trig identity to find, we could use the Pythagorean identity to find cosine. So 3/4 squared plus cosine squared theta equals 1. This is going to be 9 over 16 plus cosine squared theta equals, we'll make this 16 over 16 so that we can subtract 9 over 16 from both sides and get that cosine squared theta equals 7 over 16. Take the square root of that and get that cosine theta equals square root 7 over 4. So then tangent theta is sine theta over cosine theta, which would be 3/4 over the square root of 7 over 4. And if we flip that, our 4's cancel out, and that's 3 over the square root of 7. And we rationalize that denominator and get 3 square root 7 over 7. Identities based on the symmetry of the unit circle are called the symmetric identities. So case 1, this is the case of the coterminal angles. There's a Sherlock Holmes mystery for you, the case of the coterminal angles. Anyways, so that just says that if we add any multiple of 360 degrees to an angle, we get an angle with the same sine and cosine, right? So if I have an angle here with some cosine, let's call it theta, and some sine, right? If I go around the circle 360 degrees, I'm going to end right back up at the same place on the unit circle with the same sine and the same cosine. In case 2, if I add multiples of 180, so if I've got some angle here on the unit circle, if I add 180 degrees or I subtract 180 degrees, I'm going to end up on the opposite, the diagonal quadrant. So case 2 goes from quadrant 1 to quadrant 3 and quadrant 2 to quadrant 4. It's going to flip it diagonally. This 2k minus 1 means odd multiples of 180. So 180 or 3 times 180, right? If I go 3 times 180, I go from here to here, and then that's another 180, and then another 180, and I end up the same as if I'd just done it once. And so when I do that, my sine and my cosine both become negative of what they were, meaning if they were already negative, then they become positive. In case 3, I'm going, so if I've got some angle here, I want 360 minus that. So if this is some angle theta, 360 minus theta puts me here. So that goes from quadrant 1 to quadrant 4, and then also from quadrant 2 to quadrant 3. That's going to flip over the x-axis. Over the x-axis. And so when you reflect over the x-axis, your sine becomes negative, your cosine stays the same. And then your last one is 180 minus a. So again, if I've got some angle a here, 180 minus that puts me here. So that's a reflect over the y-axis. Goes from quadrant 1 to quadrant 2, and from quadrant 3 to quadrant 4. And so in that case, your sine stays the same and your cosine becomes negative. All right, so express each value as a trigonometric function of an angle in quadrant 1. So we always want to start with case 1 to get an angle between 360 degrees. And all of the angles on all of the cases work just the same with radians. If you do 360 degrees equals 2 pi radians, or 180 degrees equals pi radians. And it works exactly the same. So we always want to start with case 1 to get an angle between 0 and 360, or between 0 and 2 pi. So we can make this sine of 360 plus 240, and according to case 1, that's just equal to the sine of 240. Now, 240 is in quadrant 3, so we need to switch from quadrant 3 to quadrant 1. That's going to be case number 2. So we're going to make that sine of 180 plus, what do we need to add? To get 60, we need, or to get 240, we need to add 60. And so make that then sine of 60, we get rid of the 180, and according to case number 2, we make that negative. So sine of 240 is negative sine of 60, and sine of 600 is equal to sine of 240. This here, sine of 19 pi over 4, that is bigger than 2 pi, because 2 pi is equal to 8 pi over 4. So, coterminal angles, we're actually going to do 16 pi over 4 is 4 pi. That would be 2 whole loops around the circle. So we're going to make this equal to sine of 16 pi over 4 plus 3 pi over 4. This is equal to 4 pi. That's 2 loops around the circle. And so according to case 1, this is equal to the sine of 3 pi over 4. 3 pi over 4 is in quadrant 2. To get from quadrant 2 to quadrant 1, we need to use case number 4. And so according to case 4, we do 180 or pi minus 3 pi over 4. And I'm going to write that pi. Go ahead and get a common denominator here. I'm going to write this as 4 pi over 4. All right, that's pi minus 3 pi over 4. And make that sine of, lost my train of thought. All right, so instead of 3 pi over 4, 4 pi over 4 minus pi over 4 equals 3 pi over 4. This gives me pi. This is sine of pi over 4. And when we switch from quadrant 2 to quadrant 1, our sign stays the same. So according to case number 4, it's just equal to sine of pi over 4. For C, we're going to use our case number 1 again and make this. We're going to need to add 720. So if I add 360, that still doesn't get me a positive number. I need to go around the circle 2 times. So if I add negative 410 plus 360, that's going to give me negative 50. And I am going to need to then add 360 again and get 310. So this is going to be equal to the cosine of 310 minus 720. And that is going to, right, because this is a multiple of 360, according to case number 1, that's going to make, it's just going to be equal to the cosine of 310, coterminal angle. And then cosine of 310 is in quadrant 4. I need to get to quadrant 1. So going from quadrant 4 to quadrant 1 is case number 3. Yeah, case number 3. And so that's going to be equal to cosine of 360 minus what? Minus 50 gets me 310. And so that's going to be cosine of 50. When we go from quadrant 4 to quadrant 1, the cosine stays the same. So that's just cosine 50. Tangent, 37 pi over 6. And so that was case 3. 37 pi over 6. All right, we can make this tangent of 36 pi over 6. Plus pi over 6. 36 pi over 6 is 6 pi. That's 3 whole loops around the circle. And so by coterminal angles, case number 1, that's just equal to tangent of pi over 6. And pi over 6 is in quadrant 1. The opposite angle identity. Sine of negative A is equal to sine of A. Cosine of negative A doesn't change. All right. And for this example, we want to simplify sine x plus sine x cotangent squared x. And so first thing that we can do, we've got a sine x here and a sine x here. We can factor that out. So factor out a sine x and make this 1 plus cotangent squared x. Hopefully that should look familiar according to one of our trigonometric identities, right? One of our Pythagorean identities. So one of our Pythagorean identities says this. 1 plus cotangent squared x equals cosecant squared x. So take cosecant and plug that in to make this sine x times cosecant squared x. We can use our reciprocal identity to make this 1 over sine squared x. And so the sine x and one of these sine x's is going to cancel out, makes that 1 over sine x, or just cosecant x. Many sunglasses have polarized lenses that reduce the intensity of light. When unpolarized light passes through a polarized lens, the intensity of the light is cut in half. If the light then passes through another polarized lens with its axis at an angle of theta to the first, the intensity of the light is again diminished. The intensity of the emerging light can be found by using the form I equals I0 minus I0 over cosecant squared theta, where I0 is the intensity of the light incoming to the second polarized lens, I is the intensity of the emerging light, and theta is the angle between the axes of polarization. Simplify this expression and determine the intensity of light emerging from a polarized lens with its axis at a 30-degree angle to the original. So, in order to simplify the formula here, we have an I0 here and an I0 here. We can factor out that I0, make this 1 minus 1 over cosecant squared theta. 1 over cosecant theta is sine theta. So make this I0 times 1 minus sine squared theta. We also have this identity, our Pythagorean identity, that sine squared theta plus cosine squared theta equals 1. If we subtract sine squared theta from both sides, we get that cosine squared theta equals 1 minus sine squared theta. So we're going to take that and we're going to plug that in there. And so that's going to be I0 cosine theta. So the intensity of light that passes through a second polarizing lens with an angle of 30 degrees to the first, I is equal to I0 times cosine, that should have been a cosine squared, cosine squared of 30 degrees. And cosine of 30 degrees is root 3 over 2, and we square that, and that's going to be 3/4. So the light that passes through the second polarizing lens at an angle of 30 degrees to the first is 3/4 of the original. And that's it for section 7.1, Basic Trig Identities. Tune in next time to learn verifying trig identities, where we learn how to prove that something is an identity.